Well, welcome everybody. This is Mr. Bergmann.
Greetings.
And that is Mr. Sams.
Greetings.
Hey, you know, we were just talking about our childhood. And Mr. Sams and I were relating stories from when we were your age.
High school hood.
A high school hood? I didn't go to a hood of a high school.
No, I didn't either.
I was actually in a privileged high school, I must say. It was, you know, a bunch of rich kids. Although we weren't rich. I don't know how we got there. So we were military, so I don't know. Somehow we fit in a little bit. I don't know. But, you know, I'll tell you a story. Mr. Sams and I were telling a story, and I tell you the story, you know, when I was in high school. I think I was a sophomore. I know I was a sophomore in high school. I was actually telling my son this the other day. And because he's a sophomore in high school right now. And, you know, I had a buddy, and he was a single child, and so he took us. He would invite friends of his on vacation, and so that's a car.
What is that?
It's his car.
Oh, okay.
And his parents would take us camping. You don't like? Am I drawing?
Oh, it's a trailer. I see. I had no idea where you're going with that.
They had a trailer, and they took us to the lake because they had a boat. Actually, they had a trailer and a boat. They had two cars, like Mom drove one and the other. So they took a trailer. They didn't do the two things. And they'd go water skiing all the time. And so we were going water skiing a vacation because this kid was an only child and he had no friends except me. So, so long story short, I got on my bicycle. We were at the campground. I don't know if you've ever been camping, but they have like campgrounds. So Mr. Bergmann is on his bicycle. That's me on my bicycle. Okay, and I'm driving around the campground. You're laughing at my diagrams. And there was this pretty girl. And my eyes focused on the pretty girl. You know, it's really not a good idea, Mr. Sams, to focus on something else when you are riding your bicycle.
No, you always want to look where you want to go.
And see, I was looking at her because she was pretty.
Right.
You know, I was 16 or whatever I was, 15, 16 years old. Long story short, I looked down and I said, uh-oh, we have problems. Because there was this big rock because I had steered off the road a little bit. And then Mr. Bergmann's bike stopped. It's actually quite a physics moment here.
Yeah.
What does it say? An object in motion
will stay
in motion. You see, the bike stops. Mr. Bergmann flies over the top. He actually lands on his face. Right on his jaw. And I broke my jaw. Snap, crackle, pop. And then, of course, the parents of my friend Jim was his name. They had to drive me home like 150 miles from the lake back to the town that we lived in. Yeah, it hurt a lot. In fact, the funny thing about this story, they're driving me back, and they'd called ahead. This is before cell phones. They called my family and said, we're going to meet you at the hospital. They didn't know where the hospital was. And I did. And so I have to communicate with a broken jaw to the parents in the front. And they didn't have paper and pencil, and so I'm signing with my hands, and somehow I communicated with them where the hospital was. It was on Hayward Street or something, or I don't know. And I had to somehow, I think I was using rudimentary sign language. Is that an H? H? G? Yes, it's an H. All right, hey, H. All right, H. All right, what's the next letter? We were playing like, what do you call that? Charades. Mercy. It was an interesting day. So next time, Mr. Sam's going to tell you about how he hurt himself.
I am the only person in my high school's history to have a speech and debate injury.
Injury.
Yes.
So he had injury. So we will have to hear this story. I think it will be interesting. All right. 3-minute story there. Okay, if you needed to fast forward to that, hopefully you enjoyed that. Okay, acid-base indicators. Okay, today we're going to learn about acid-base indicators.
Yeah.
We've known that there's two ways to indicate that you're at the end point of a reaction, right?
Yep.
It's the steep portion of the graph or whatever. And the second was the indicator. Okay. But how do indicators actually work? So there's some chemistry behind indicators. Yeah. All right. Actually, I guess I've already done this. How do you know if any point is reached? Colorimetrically, that's when you see a color change, which I just sort of alluded to.
Hence the name.
Colorimetric. And the pH meter is the center of the steep portion of the graph. It could look like that, or it could be the opposite deal. Okay, so we've sort of already learned that. So I don't think that's really that important. But how do you pick an indicator? Which indicator do you actually use?
I like the one that makes the nicest color.
Oh yes, the pretty one. You like the pretty one. It makes it very pretty.
Yeah.
That's not a really good idea, Mr.
Yeah, it's not a very good way of picking.
It's not going to work. Okay. Actually, the first thing you would do is actually do the indicator graph thing, the pH graph. So you would do this graph, and then you would find the pH at which it changed. Now remember, we learned that they're always not 7,
right,
unless it's a strong acid, strong base. This example that I've drawn is probably a weak acid versus a strong base, and the pH is greater than 7. But we also learned in our last podcast that if I had a weaker acid, it actually might do something like this, and then the pH would be even much greater than 7. So the first example I just did a minute ago, well, this might be a pH of, say, 8.5, and this one would be a pH of 10.5. So which indicator do I use?
Now we got to find one that changes in that range.
So then you have to use a chart. So if you look at the chart in your book, it looks something, or in your handout, I should say, but it looks something. It looks just like this. You're probably, you don't have the color version. You have the black and white version. So hopefully we have the colors written out. Ours is in color because it's pretty. Okay, but you get the idea. So if I knew something would change at a pH, if I did the pH graph, so let's go back to the one I had here. This one, let's say, we figured out would change at 8.5. So it changed to 8.5. Which indicator would I use?
Thymol blue, second transition, up at the top or down there. Phenolphthalein would be a good one.
You wouldn't use one that has second transition.
Yeah, that's probably not good. Yeah.
You usually want to do one that has one transition. That you would. That would be fine. Actually, the interesting thing about this is if it's got a really steep curve, frankly, your choices. If let's say this pH right here is 4.5, and this one is 10.5, you're looking for something that will clearly change
in that range.
Anything in that range, and so we have lots of choices that we could make here. Frankly, I said 4.5. I think I would choose Brome Crescel purple.
Oh, that's a pretty one too. See, it fits my description as well.
All the way up to maybe I might use
maybe phenolphthalein.
I would use phenolphthalein. Yeah. Phenolphthalein is a great one. That's the one you're very familiar with. Of course, it's colorless in an acid, and you're looking for something that's a strong color change. This isn't a bad one. The Crescel red goes from yellow to purple. That's probably something that's pretty noticeable.
The easy ones to see are going from colorless to something colored.
Yes.
Those are the easiest to see.
Now this one, red to yellow, is sometimes that transition is hard to see. So for the natural red,
like, is it still red? Is it orange? Is it yellow orange? Yeah, those are kind of.
So those are some interesting things. So or my second example, which I think I actually gave you examples. Did I not? Oh, I did.
Yeah.
I should probably use this. Well, we'll use this one. If I have 10.5 as the color change, probably I'm going to use this thymol. Phthalene probably or something.
Yeah.
You get the idea, I think. Let's take a look at a couple of examples here. So if I have the graph here, which indicator would you pick? Would you choose phenolphthalein or methyl orange?
Phenolphthalein.
That's the reason you would, of course, is because methyl orange changes after it's reached the equivalence point. So methyl orange would be a bad choice.
Yep.
What about this particular one right here?
Yeah, that's still on, even though it doesn't touch the equivalence point, it's still on that really steep part of the graph, and so methyl orange is going to be just fine.
So this case, you choose methyl orange. Yeah, it's at the bottom end of the graph, but it's still going to work just fine. And one last one. What about this one right here?
Well, it depends on which equivalence point you're
looking
for.
You see, you're looking at, this is a diprotic base. A alkaline base, whatever it's called, because it's got two different steep points. So if you're looking for the first equivalence point, you would take phenolphthalein. If you're looking for the second equivalence point, you'd use methyl orange.
Yeah.
Okay, now how do these things work? How does an indicator actually work? Do you know this? All indicators
are weak acids or bases.
Actually, they're all weak acids, I think, aren't they? No, some are bases. Yeah, you're right. What happens is, if I have a weak acid, we'll call them HIN, where IN is the
indicator.
The indicator ion, if you will. It breaks apart into hydrogens and the IN negative. Now, this is assuming that it's a monoprotic acid. It could be diprotic acid, too.
A lot of them are, actually.
And a lot of them are. And if, let's say, that the HIN is blue and the IN negative is green, then what would happen is, of course, is as you add base, this forms water.
Yep. And then we have Le Chatelier's principle kicking in.
Which we haven't really talked about yet with these guys. Yes, we have. Yeah. Le Chatelier's principle kicks in. You're right. And so that takes away hydrogen, which drives this reaction back to the left, and it's going to turn...
To the right.
I said that wrong, didn't I? Yes, it'll drive this reaction to the right, and it will make this solution blue. Green. I'm really good at this. Okay, I'm not getting this figured out. Okay, and conversely, if I were to add hydrogen to this... All right. If I were to add, this is getting confusing. So if I've got HIN turns into H positive plus IN negative, and I forget my color scheme I made up here. Blue and green. This is blue, and this is green. So if you were to add am I ADD?
I don't know.
H positive, it would drive this
Probably
reaction to the left, and that would turn this blue.
Right.
And so that happens at a particular pH. And so it's just, I think the key thing to understand is that they are weak acids and bases, and they have their partners, and each partner has a color. Sometimes one of the colors is colorless, or whatever, and many of them can be, say, sort of diprotic. All right, let's do an example here. The equivalence point of a titration is 4.3. Which one do you pick? Now, notice here we have a list of their Kas. So on the previous ones, we had like this cool picture graph thing, but I don't have the picture graph, but I'll bet you can figure out this one. It's very uber simple. Basically, where this is 4.3, what you're looking for is the one where the pKa is closest to, in this case, 4.3.
Yep.
Now, I'm not going to get a calculator out and do each of these.
Yes, that's going to be
because let me just do it in my head. If this is 10 to the minus 11th, the pKa is going to be about
a little less than 11.
Like 11. This one's going to be like a 9. This one will be like 8. Actually, it's going to be a little bit less. So this is 9. This is probably 8.7 or 5, 4. Who knows? Something like that. But it's a bit less. This will be about like 6. This will be about like 5, and this will be like 2. So if it's 4.3, if we're looking for something that's in the 4 range, remember it's always a little bit less. So endocrine black is our answer in this particular case. They're not terribly difficult. You just take the negative log of this, or you just look at the exponent. The one closest is the wiener. Okay? All right, hey.
All right, something new.
New
We're kind of shifting gears.
New topic.
Not acids and bases anymore.
We are done with acids and bases?
We are.
Completely done?
Yeah.
If you haven't figured it out by now, ask lots of questions. Because you probably will need them.
Yeah. Now, this is still an equilibrium system.
Now, let's actually talk equilibriums right now for a second. There are different varieties of equilibrium we've been talking about so far. Before we talk about this, we've learned about Kp, what's the P stand for?
Pressure.
Pressure. Okay, and we found Kc.
That's just concentration.
Concentration.
Sometimes
By the way, also
K.
sometimes just K.
Yep.
We learned about Kas. That'd be acids, right? Kb's, that'd be bases. Kw, that's sort of special, that K of water. And now we have any more?
No, that's it. Now it's just Ksp.
We have one more K. Now it's capital K. Small k, remember, is a rate constant. Big K is equilibrium constants. We have one more K. It is called the Solubility Equilibria.
Yes.
So it is the study. Actually, the SP, by the way, stands for solubility. Solubility.
Bility.
Product. What's product mean?
The thing that's produced.
Well, not in this case.
Oh, multiplication.
In this case, the product reference is the multiplication. It's a mathematical term, times. Okay. Now, the KSP is kind of a weird thing. Is the study of insoluble. It's the study of the solubilities of insoluble ionic compounds.
That sounds a little contradictory to me.
That does sound contradictory. We're going to study the solubility of things that are insoluble.
Right.
What? That doesn't make no sense.
No, because nothing's actually insoluble.
Yeah.
No such thing.
Now, when we say solubility, remember, we're talking about naklonosos. Things that we've memorized are soluble.
Right.
All sodium compounds are soluble. All chlorides soluble. All nitrates. All sulfates with exceptions. And da-da-da-da. And then
everything else is insoluble.
Not soluble. But guess what? We've sort of...
We lied.
Lied to you, yes.
We're horrible people.
Well, because everything is actually, to some degree, soluble.
Right. So all those things that you learned as insoluble, keep them in the back of your brain that they're still going to form precipitates if they form products. But they still dissolve a little bit.
So everything is at least slightly soluble.
And some things it's like ever so slightly, and infinitesimally slightly, but it's still slightly.
And this is the study of that slightliness.
Yeah.
Is that a good word?
Slightliness. I like it.
Slightliness.